Hello, how are you?
Good. How are you?
Good.
Just want to make sure you were good in here. Everything's
So far, so good. Looks like I managed to get the slides. Slides
wonderful.
uploaded. Can present.
Easy. It's just in case. Awesome. Okay. Well, let
Okay.
me know if you need anything. I'll be back. I'll pop in and out. And
Yes, thank you. I think I'm. It's nice to practice. I
yeah,
forgot. I keep forgetting how to do that between meetings.
yeah, I know. Well, and it's always like a little different. I feel like so.
Yeah,
Yeah.
like where is the?
Yeah.
Yeah,
Well, perfect.
cool.
Awesome. Wonderful.
Okay. Good morning. Welcome to the best session of IETF meeting, the first and the best one. As you can see, I'm not Warren. I'm probably a poor substitute for him, but I'll do my best. Unfortunately, he could not be in this room today. He got COVID, so I feel sorry for him. He's stuck in the hotel room. So, first of all, how can I present this? So, up works. So, if you don't know what you're doing here, this is an IPG meeting, which is informal gathering. We don't even have IETF badges yet. And we normally talking about operational issues or something related to operational issues. Usually it's happened to be IPv6 or DNS or RPKI, but I guess today we have few presentations on other topics as well. Uh, sorry, you now have to suffer just one more slide in Comic Sans. I made those slides just late last night, so not everything is here. So just a reminder, if you're speaking on the microphone, asking questions or making comment, please state your name so people know who you are, even if you are famous. It doesn't hurt. Masks supposed to be worn all the time. You may remove them if you're speaking, actually, briefly. And let's look at the agenda. Oh God, what's happening? So, actually, this is not up-to-date agenda. Randy said he will be presenting in the working group and not here. So we don't have presentations about our PKI today. So we'll have two talks about extension headers. Great. Uh, Presentation about telemetry, presentation about digital map modeling, and something about time per meeting. So let's start from the first presentation. Nalini, you are first. Let me try to get the slides. Uh, okay. Oh, ah,
Am I okay to take this?
yeah, if yes.
Next, please.
Ah,
Okay. Yeah. You guys hear me okay? So, yeah. So this is no.
I
Testing.
is
Testing. Oh. Thanks. Okay, so this is a continuation of something that we have been studying for probably the last year or so, and there's quite a bit more left to go on this. We've got some kind of interesting results. So I wanted to thank some of the people who've been supporting us with both giving students to do the testing and also financial support. Okay, next, please. Okay, so I'm just going to review where we were and then start with the new stuff. So I'll go through this new stuff, the old stuff, really quickly to catch people up who may not have heard some of the other things. So this is what we're doing is we're trying to figure out where, if extension headers can be used on the internet, and if not, exactly what is the problem and why. And our motivation for this is that there's a particular extension header we would like to use. So next, please. So what we did, we used the 1980s kind of topology, which is we're connecting directly into the internet without a cloud service or CDN or anything like that, and we put it in locations throughout the world so that we would be going across the core of the internet. And how we did it is we modified the kernel to send an extension header with each packet. Okay, next please. And you can see we sent FTPs. The other thing we did, we sent real data, not fake scapy packets or anything like that. Next, please. As I said, this is all old stuff. And you can see from doing the packet traces that you can see that we have not just our destination options, but fragment headers being passed across the internet. Next, please. And so the bottom line, we have traces available for all of this, everything across the internet, given that it's a bare bones topology seemed to work. Next, please. So this is what we're talking about, very simple topology. This is not the topology most people have today. Next, please. So then what we did, this is where we're now really getting into the new stuff. What we did now is we moved the server, our server behind a CDN. What we have is we have a client with an OS that we've modified. We have a server with an OS that we've modified. They both will send extension headers with every packet. So what you do is we just got a free thing from the CDNs, you know, a free service, and we moved our web server behind a CDN. So now what happens, and it's a little complicated. So what you have to do, CDNs, of course, let's go to the next slide. You'll kind of see the topology. Yeah. So what happens when you move behind a CDN is the CDN now is going to do our DNS resolution. They also have like a bunch of edge servers all over. So, you know, if you're in Bangalore, you're going to go to the Bangalore one. You're not going to go all the way to San Jose. That's the idea. So you've got a clump of internet on both sides. Internet from the client to the CDN edge server, internet from the CDN edge server to the origin server. So there's two clumps of internet that you could be going over. Next, please. So now this is the new stuff. Let's go. So why are we looking at CDNs so much? Because many of the high usage websites on the internet use CDNs. And so the behavior of CDNs will have a disproportionate impact on how things go, okay? And what we want to do is we want to be able to say, where can we count on EH as being pretty much okay to use, and where can we not, and why? Not just that they can't, but why, and what we don't know. Okay, so next, please. So the way that a lot of CDNs work is you can have either, you can say, you can just resolve my DNS, and then if they just resolve DNS for you, you've got the standalone, you know, service. They're not doing your edge proxying for you. That's one way. Of course, why anyone would pay a whole ton of money to have, anyway, so probably you're not doing that, all right? So you probably want the proxying functions. So, but you can say, this is the actual screen where you can say, and we set up a bunch of different scenarios, some quad A, some, you know, just IPv4, so forth. So let's keep going. I'll show you what happens. Next, please. So what do we have? We have a client machine in Singapore. It's dual stacked. It's got a V4 address and it's got a V6 address. We can do either curl or ping with it. And all of that is going to have an IPv6 extension header attached to it. And then the server that we put behind a CDN, we put it in Newark, and it's dual stacked also. And it's got, we did a bunch of different things. We put it on V4 only, V6 only, and so forth. But we've got the capacity to be able to change stuff around. Okay, next, please. And these are our DNS definitions. And so you can see we have an A and a quad A for both of those domains. And all of that is resolving to, this is from the CDN. The CDN is doing all of this. Okay, next, please. So what we did is we just did a curl. We have Apache running on the origin server, and we just did a curl, and we didn't get anything. And so we're like, good heavens, what happened? Next, please. So, of course, we can do packet traces at the same time. What we're seeing is we're seeing that we're sending the extension header, and port 80 is answering, even though the SYN had the EH. So, it did resolve. It went over there and the SYN resolved, okay? So that means we got all the way behind to the CDN. Let's see what else is going on. Next, please. Then recall, that's doing IPv6, okay? And so the source address here, this is Singapore. We sent the TCP SYN, and the dest address, it ends with AA01, and that is the CDN address. So we are going to the CDN edge cache. Our origin server ends with 1527. So we are being proxied. We're being proxied. So that's really good to know. Okay, next, please. Because this is where it gets confusing too. Next, please. So let's make sure, and we look up that address, that the edge address. It is this indeed the CDN. Okay, next, please. So when we take a trace on the other side, the shocking thing, of course, is that we're seeing IPv4, and we're like, good heavens, what's the problem, okay? And so there's no response to the SYN. Remember, this is a dual stacked. We have V4 and V6 DNS, V4 and V6 on the web server. And what we did initially, we said because the CDN provider said, just turn off don't make it listen on V4. And then just have the web server listening on V6. So we said, okay, let's do that. But what it did, it preferred V4 anyway, and so it didn't respond. Preferred V4, it didn't respond. That's an interesting thing. So let's go down. And you can see from the forward packet that it was going on V6, it got forwarded, and then transferred over so that it was proxied over to V4. So, okay, so next. And so this is an important thing to know. If you have V4 and V6 DNS, it's going to prefer V4. Interesting. Let's go down. Next, yeah. So then we said, let's take out the DNS definitions. So we're going to force it to go over V6. Okay, so let's see what happens. So we did the curl. Curl comes back this time. All right, let's see what the packets look like. Okay, next, please. So from the client side, we can see that we are sending our extension header. It's not being blocked by the proxy, but we're not getting extension headers back from the server, even though it is defined to send extension headers back. Okay, so next, please. And on the server side, yes, this time we are getting V6. We are not seeing the extension headers though. So what is happening is if you do V6 only, yes, it goes V6, but you get nothing, you get no extension header to the origin server. Next, please. And we are using the proxying function. And yes, you can see indeed, if you resolve these addresses, it's the CDN. Next, please. And we look it up, indeed, it's the CDN edge cache that we're using. Next, please. So what happens if you do V6 only is that the extension header works over to the CDN edge. I mean, the packet is not dropped, but packets with extension headers do not go to the origin server. And this is true for all the CDNs that we tested. This is actually as good as it gets for the CDNs. Some CDNs don't even, if you do V6 only, they won't even work. So this is the best that CDNs can do at this point. They will go to all the way through, but not to the origin server. But on one hand, it is an interesting thing it to know. It's like if you can be sure that it'll go up to this side and then you know it won't go to the other. I mean, that's at least something to know. And one of the things we're looking at is some of the CDN edge servers have an API. They have like an API gateway and this and that. So we're looking into what we can do to modify those at the CDN edge. The idea being is that we know exactly how far it'll go. Okay, so next, please. So then we start playing around. We start doing some more curls to another DNS. This is our V6 only. Next, please. And it worked. But this time, what we did is we did it to the one that's using DNS only. We let the CDN do only DNS for us, and it worked. Again, why anybody would ever do that is beyond me, but it worked. And let's look at the packets. If we look at the packets, we see that we are getting destination options, our extension headers coming from both ends, and this is great. Let's look and see what's going on. So next, please. What we can see is that the Singapore address is us at ABEE, and our destination address is 1527. As we thought, the CDN is not doing any proxying for us. If it just does DNS, it all works. So now, next, please. We're now back to the simple client server world. And on the server side, yes, we're seeing everything just as we should. But again, let's go next, and we're back to the same standalone 1980s world, and that all works, and we knew that. And even if the DNS is being resolved by the CDN, that's the truth. Okay, so let's go next. So, yep, if you bypass the CDN proxy, then it all works. Well, great, right? Okay, okay, next. So one of the things we did, we've been working with a couple of the CDN providers, and some have been very, very transparent with us and said that they found a bug in their load balancer code and they fixed it. And so we did tests before and after. So in November, when we did the tests before they did the patch, this is the Alexa top 1,000. What we got is about 31% of the sites responding to packets with extension headers. And after they did the fix, now 100% respond. That's excellent. Next, please. And this was another CDN provider. And now before, in their first test, they had 16% responding, and now they have 99.4% responding, almost everyone. So these people, it's an interesting thing, you know, it's like they've certainly done something, I bet. We have had some conversations with them and what they've done or not done, and whether they've seen IEPG presentations or they know that people are interested, whatever. I mean, I don't care. It works now, you know, that's really good. It doesn't work to the origin, but they're not dropping packets. One of the things I'll say about this is that there are a few companies that disproportionately impact the behavior of what happens on the internet. CDN providers are one such. And there's two other people that we're working with, two other companies who are very large on the internet, and having conversations with them to say, you know, why are you blocking stuff? Is it policy, or do you not know, or is it a bug, or what? Because, you know, I think, as I say, it's interesting. Okay, so next. So again, what we want to do is, where can we use it and how? And where can we not use it? Definitely on the other side to the origin server of the CDN. You're not, you know, I haven't seen anybody even jumping up with the CDN providers. If there's any CDN providers in the room, we would be happy to work with you to help you test. You know, we're chasing up a few other things, whether we can co-locate, so on, whether there's other devices that seem to be intervening. But as I say, the initial stuff, the initial results that we have appear to be that it's at the destination end is where we're seeing the blockups. We don't appear to be seeing things blocked in the core of the internet or by ISPs. As I say, we've still got a lot more testing to do, but this appears to be our interim results. Next, please. So one of the things that we should think about, and I will bring this up in V6 Ops again, is a few questions. Do we need a BCP for CDNs? Should CDNs prioritize V6 over V4 and DNS? Right now, V4 is being prioritized. Should CDNs be encouraged to send extension headers to the origin? As I say, I don't know what is involved there. I don't know their code. Should there be a BCP? So we should think about that. Another question really is, there are some CDNs who will flat out not even do IPv6 to the origin server. And now that's interesting because again, some of this stuff I hear in V6 Ops about V6 only, this, that, and the other thing. Well, you might want to talk to some of the CDN vendors before you start talking about V6 only. They're doing V4 only. So there we are. Okay, next, please.
I think it's the last one.
Is it the last one?
Yeah.
So, yep, there we are. Questions, thoughts?
Okay, before I open a queue, I would appreciate if people who are physically in the room will join virtual queue if possible, because it makes much easier to manage the queue for the chairs. Thank you.
There's a switch on the mic. Morning, Anthony, Liquid Telecom. I can answer your question on the CDN stuff. It is because of the proxy, because there's just two connections. You don't have one connection passing through, so you'd need the CDN provider to do exactly that, put the extension headers on the proxied connection. And to talk to the V4, V6 backend, it's just been a case of, from what we've seen, it's just most network stacks do tend to prefer V4 only when they see both. And I know from personal experience with Cloudflare is that their whole selling point was, hey, we can V6 enable you even if you're not V6 enabled on the back end. And that was one of their USPs back in the day.
No, thank you. Yes, of course they're doing proxying. They're doing two different connections. It couldn't possibly work any other way unless you're just doing DNS only. You can see that from the traces. You've got a V4 trace. The only way you can do it is if you've got two separate connections and you're rewriting it. Yeah. Again, I have not looked at the code. I don't know how difficult it is to pass the extension header. I'm just saying, as a group and as a community, many other times we prefer V6. And in this case, apparently we don't. Any other questions?
Okay, I guess I'm the next in the queue. So I have comment. I think you're actually talking about two different problems, right? One is what CDN is doing inside for the second connection. Is it V4 or V6? And in general, it should be transparent to the user because it's their network, it's their design, they could do different things there, right? And it should not even affect, for example, my ability as a V6 only user to reach the server, right? Because CDN is doing proxy. I guess you can have your web server listening on V4 only, and I as a V6 only user would still be able to talk to it because of CDN doing the terminating my connection and opening a new one. So I think it should be left to CDNs to decide how they do internal stuff. And obviously, I second to what has been said. I think it's expected for CDN to open a new IP TCP connection, right? So I don't know if we can expect IP header parameters to be propagated to the next connection. I don't think the stack could even know if it should be doing it or not. I think what you're talking about is probably creating a new property for extension header of a given option, which should indicate if it needs to be propagated in proxy or not, but it looks like a bit complicated to me at this stage.
That's very interesting. I mean, I actually have written some proxy code, and I can do this. I'm happy to share my code with you. It's relatively non-trivial. I mean, they're relatively, it's not terribly complicated, It's just a question. I think there are two different questions. There's two different questions, what should we do about DNS? And then the V6 to the origin. There are some CDNs that won't even do V6 to the origin. I suppose I felt a little bit more like that's more of a problem than not passing the extension headers. Because if we can be sure that we know that the CDN edge is going to, that's as far as you're going. That's fine too, because one of the things that I'm doing is like, we want to do performance measurements. And if I know 100% this is how far it goes, then I can say, Mr. CDN, this is your problem. You're the one who's proxying at the other end. And so if there's a problem with response time, it's over there on your side of the network and your proxy. At least I know what things are. I'd rather have some stability. That's what I want.
For the timekeeping purpose, I am closing the queue after Warren. For some reason, I do not see a button to do this, but I declare that there are 3 people in the queue and it's all.
Hi, Neil, Jeff Haas. So this is all good stuff. What cores are you tracing over for this work? Because one of the things I'd be concerned about with this is that, are you having trouble understanding me?
No, I'm not. Yeah. What am I tracing? Yeah.
What network cores are you actually going over? Because one of the things I'd be concerned about methodology-wise is that a lot of larger service providers tend to be somewhat monolithic in terms of what stacks they run and how new their boxes are. So I would expect this, if this is going to be working, hopefully it'll be working on mostly newer boxes, but if you start going over older networks and things start breaking, that might be a concern, and that sort of turns your methodology question into what percentage of the network is expected to work to support your use cases.
Yeah, I think if I understand your question, it's kind of like, let me restate it. It's like, I think, are you asking like, are we going from San Jose to New York, which is possibly using newer equipment, although with the US being a 4th world country, I don't know, but anyway, or are we going, to, somewhere in one of our rural villages in India? Is that kind of what the question is?
It's in the family. So like if everything was going over, like say AT&T, if AT&T had no problems, that's not necessarily proving this works. It just proves AT&T is not a problem child. If you're going through maybe a number of smaller networks that might be running older equipment, that may be a different indication.
I totally hear what you're saying. And one of the things I will tell you is, and we need to do more, is I got fixated on CDNs, because we're trying to go for like the heavy hitters, because the big sites, there's a disproportionate impact from CDN behavior on some of this stuff. And we have not done all kind of testing using all kinds of different ISPs and to a million different locations. We have gone across the core of the internet using various things, but it's limited. And I will say it's limited. I will tell you too, is that if I felt like it was ISPs that were the problem, and that's where we were kind of seeing a bottleneck. I mean, even I would give up. I'm kind of like, okay, this is not a problem I can solve. But I don't, and as I say, I'm not ready to say this, but I'm feeling more and more that there's a relatively few number of players, and they appear to be at the destination. But I'm not ready to say that, but I totally hear what you're saying though. Yeah.
So
thanks.
a final comment on that. Have you considered talking to to RIPE about their Atlas probes and see if you can get the stuff installed maybe there?
Yeah, that's a real good question. That's a real good question. Right now, as I say, yes, that's a very good idea. I want to fixate some more on the CDN. As I say, I just have some proxy code myself. You know, I was just writing that for another nefarious purpose, and I don't know. Yes, you're right. Yeah.
I think we might hear later on today something about internet propagation data. So just for sake of time, let's be brief.
Sure.
Yeah, it is the Kok, right by NCC. I'm not working on Atlas, by the way. So when you use a CDN, you often use that not only for proxying, but also for caching. And now I'm asking you to postulate a bit. Because of the CDN, you often cache a different version for different HTTP requests. So in this hypothetical situation where you would have end-to-end extension headers, would you want the CDN to cache a copy for every different permutation of extension headers, or what would you expect?
Yeah, that's a very good question. It's a very good question. And I will say, I haven't thought it through yet. I'm just, right now, what we're trying to do is like, what's the scenario? You know, where are we exactly in terms of what the topology is and where does it stop? But you're asking a very good question, and I don't know the answer. I haven't thought it through yet. Yep.
Okay, thank you.
Okay, I think we have Warren in the queue. Last one.
Hopefully audio works okay. So, I mean,
Yeah, we can hear you.
great. IPv6 extension headers are an IP level construct, right? Like they're carried as part of the IP packet. That's where they live. What you're talking about here is a web proxy, and that works at the web layer. So I don't really see how or why extension headers would be propagated. It's not that we propagate like the TTL or the original packet checksum into the web layer. They're completely different layers. You're making a TCP connection from the client to the proxy, which terminates the IP connection and then makes a new connection and shuffles just sort of the layer 3 data through. So you're trying to kind of cross the streams here. If you're using something like ECMP load balancing instead of proxying, then maybe EHs would go through. But specifically what you've built here is a web proxy, or what you've asked for is a web proxy. And so they're completely different layers. Like having the extension header propagate just sort of doesn't make sense. It's the wrong layer of the stack. Oh, sorry.
I hope you feel better, Warren. No, actually, I believe it's probably more complicated than that, Warren. I'm using proxy as a stand-in. I think they've got a number of different pieces of equipment there. The reason I say that is that one of the folks we worked with, they put a fix into their load balancer, and that was what cleaned up a bunch of the extension headers being dropped. I totally hear what you're saying, Warren. I'm not sure that I'm ready to take any kind of position on that. I have to think about it. I think one way to look at it, I suppose, is if we know 100% that we're terminating at one of the edges, and then you can reliably get measurements to the one end of the CDN cache and maybe the other way. You've got another end of the CDN cache that's facing the server side. If we can reliably get measurements from both of those two things, because the reason I'm doing all this is I want to be able to do performance measurement for my real business data. I mean, I'm not doing this, just so I can do IEPG presentations. The thing is, I mean, we need this thing to work for our business needs. And I hear what you're saying, Warren. I don't think it's a pure web proxy. And I would like to sit down with the CDN vendors some more and understand what that is. And again, I don't want to, divulge on, digress on proxies. I've been more involved in proxies lately than I would like to be, be doing that. Yep. Okay. So
Okay.
thank you very much.
Yes, thank you very much, Nalini. Very interesting presentation. So the next presentation is Thomas on telemetry. Okay, let me start sharing the slides. Okay. Stop. Share preloaded. It's this one? Yes.
Yes, perfect. Good morning, everybody. So I will speak a bit about network telemetry, specifically about Yang push and integration into data mesh, big data, and the challenges we face as network operator. Next slide, please. So starting with an example, for instance, if we want to monitor a layer 3 VPN service in a network operator, first we need to understand how the layer 3 VPN service is decomposed. So we have interfaces, we have traffic which is flowing, we have BGP peerings, we have paths, prefixes, and first, basically, when, for instance, a link goes down, that link basically triggers changes in the network. So, for instance, a peering goes down, prefixes are withdrawn, and then depending on whether we still have a forwarding path or not, either packets are being dropped or being rerouted over a different link. And depending on what kind of network telemetry subscription I have, for instance, if it's a periodical or a not change subscription, or whether I use aggregation or not, basically the data I'm subscribing to is not arriving all at the very same time. So I need to make sure that my alert system basically takes that all into context. So at the end, when I observe these things, so when I see there is a change in the management plane on top, there is a change on the control plane as well. So my network is converging, and at the same time, I'm starting that the traffic is being dropped. The more I observe on the network, the more I'm being concerned as an operator that something is going wrong, as compared if I'm just not receiving packets anymore. Next slide, please. So to take this example, for instance, where I have two VPNs, one is redundant while the other one not. And you see basically at the top, there is like the overall concern scoring, which is basically adds up depending on how many perspectives, how many things I notice in the network. And like if just the topology is changing, I'm not much concerned unless I'm starting to drop packets. Next slide, please. So from a network operator aim perspective, so I'm aiming for an automated data processing pipeline, which starts with Yang push and consolidates in a data mesh so that I can perform network analytics. I want to use for operational metrics, whenever possible, IETF-defined semantics. And the analytical metrics which I'm generating, basically with that, I gain actionable insights on my network. We achieve this, we achieve this by basically producing metrics which have timestamps where the timestamps relate to when the network events were observed on the network. We need, in order to have a data product SLO, we need to be understanding basically the quality of the metrics being received from the network. So whenever we are observing loss or delay on those metrics, and in order to do that, we need a host name, a publisher ID, and a sequence number so that we can measure that, so that we are sure when metrics not arriving that is not a problem of the network itself, that is a problem on the data processing chain. And we need to make sure for a later closed loop operation that these metrics needs to be unchanged and that we learn automatically the semantics from the network and control these semantics end to end. Next slide, please. So if we look a little bit how big data has been evolved over the last few years, basically it's a bit similar, or it reminds me like how networks are organized. So basically in the very beginning, like we had like different proprietary data warehouses, where at one point we said we need everything to consolidate in one big data lake. And then let's say the real-time aspect was being added, and we named it Kappa. And now we understood basically by consolidating everything and throwing into a big data lake, actually it's quite difficult to manage, especially if you have various teams working with that data. So now basically it goes back that you actually go more in a data mesh fashion, where you actually organize yourself in different domains. And when you do that, interfaces are really important. So we need so-called bounded context, where we have well-defined semantics. And for operational metrics, that the organization should not basically redefine the semantics itself. It should use the semantics from the network, where IETF standardizing them. And for the analytical metrics, we need to make sure that inside the organization that we are defining the semantics. Next slide, please. So looking at Yang push and dividing them, what we have on the operator side and what we have on the IETF side, we can divide it between the transport protocol, encoding, how we are subscribing, what metadata we have, how we are doing versioning, and then the Yang module itself. And at the moment, at IETF, at the NetConf working group, and also at NetMod, we are working on finishing the standardization on the transport protocol. There are now a couple of drafts, which I will describe in more in detail, which are adding the necessary metadata to actually automatically integrate it into data mesh. And then on the versioning side, we are getting into semantic versioning. So that enables us at the end to understand whether a Yang module is evolving, that if the new Yang model version is backward compatible to the previous one or not. Next slide, please. So looking at that picture, basically we have on the data industry, which is very advanced in this topic of semantics, where IETF, I think, made a pretty good progress. But if we go to the reality, what's currently happening on the network vendor and operator side, I think there is still a lot to do. So ultimately, where we are going to is we have an API to the network where we do the configuration, which is NetConf. We have a data modeling language, which is Yang, and we have Yang push, where we are actually getting the metrics from the network. So it's a cycle between two Yang data stores, one on the network while the other one in the data mesh. So the operational metrics, the master is on the network, while the configurational part is on the data mesh. And we just need to make sure that the cycle is not broken. Next slide. So as I said in the beginning, so basically data mesh, it's about having different domains with the bounded context, and we have SLOs on data products. We need to define semantics so that at the end we have, so we can describe the difference between a counter or a gauge or an integer. We need versioning to ensure that our data processing pipeline does not break, so that we can say that this new version is whether it's backward compatible or not. And we need basically uniquely identify the publishing process, which is sending us the Yang push messages, with sequence number so that we can measure delay and loss. Next slide. And we are that serious about marrying the two protocol, messaging protocols, Yang and Apache Kafka. Next. So let's start first with the netconf notification header. So it was in RFC 5277, the XML schema has been defined. What's missing is a Yang model. This is what we are addressing with this draft. Next slide. The next point is adding the host name, the publisher ID, and the sequence number. The host name is quite important because today, basically, what's happening at the network operator is when we receive a Yang push message from the network, we have to actually add that information on the data collection. And when you add that information on the data collection, actually you do not have semantics for it. So basically now you're adding a proprietary information to it. And when you forward that message, basically the semantics are no longer matching to what you have subscribed to. So with that, we're adding that information to the netconf notification header. And next slide, please. Now we come to the next part is, so the event message itself has a timestamp. So we do know basically when the message was being exported, but that does not tell us really when the metric was being observed on the network. And here with this graph, we are distinguishing whether it is a periodical subscription or if it's an on-change subscription. So in the case of periodical subscription, it's basically the moment where you actually pull the information on the Yang data store, while in the on-change subscription, there we distinguish whether it is on-change or if it's on-change sync on start. So on-change sync on start means basically when the Yang push subscription is being established, we want to actually understand from the past when the interface came up originally, while the on-change subscription basically only tells you at the moment when the Yang push subscription has already been established, at that point in time when the interface state changes actually happen. Then going next into the versioning, the revision, and the revision label. So the revision is what we already have since day one in the Yang model, so that we can identify whenever there are changes between the Yang models, where the revision label is actually giving us semantic information, where we understand whether the new Yang model is the new Yang version is actually backward compatible to the previous one. And here we want to be capable of actually, when we are doing the subscription, to define to which, not only to which XPath, to which Yang model we are subscribing, but also to which revision, or we want to at least define we need to be compatible to that revision. So when later a software upgrade is happening, we can make sure that our that the Yang model we subscribe to is actually backward compatible to the previous one. So we do not break the end-to-end data processing pipeline. And of course, the next thing is also when we are publishing the message, we want to understand not only to which XPath this message is actually belonging to, but also what revision and revision label it is. And therefore, for this purpose, we are extending the so-called subscription state change notification message, which has already this metadata in, and we are extending it with revision and revision label. Do you realize the gaps in Yang push and how we resolve it? If you are interested, first of all, in the NetConf working group, we are presenting this draft. We have also on Wednesday a so-called side meeting where we also show the other side, on the Kafka side, what kind of extensions we need to do to actually integrate natively Yang into Kafka. So at the end, a network engineer can go to a network device, subscribe to an XPath, and there is no more a manual post-processing needed. The data can be directly ingested into a time series database. And with that, basically, we define the standardized bound and context. It's no more important who is collecting the data, as long as basically they're following that that way of collecting the data from the network, keeping the semantics unchanged. We have a clear bound and context there. Questions?
Yeah, I see Dom in the queue.
Cool.
Hello, Thomas.
Hello.
Tom Hill from BT. I'm very impressed with your work over many different IETF meetings, actually, many presentations. You've been blazing a trail, which I think is quite fantastic and quite leading. I have some questions around models, Yang models in particular. I think first, my first, to try and put this into context, I'm curious how many vendors you're working with simultaneously to drag this telemetry from. And my second question in part here is, and I know we're at an IETF meeting, have you found any benefit to the open config models?
So
as an interim step, perhaps.
Right. So so I'm talking to quite a few network vendors, and I think let's say the problem space is twofold. One is basically getting let's say having the right protocol to expose Yang push. So it's let's say today basically every vendor is just pushing JSON messages with some sort of metadata, and you basically have to make sure that you're covering all those different implementation and somehow make it work into big data. So this is what we're trying to address here. But then, yes, the next step is basically going to the Yang modules itself, having every operating system vendor having different Yang models is a challenge, yes. OpenConfig is certainly like let's say a first step in that direction. But what we saw there as well is basically the same thing we see with Yang push itself. So if you have OpenConfig platform, for instance, not every vendor is implementing OpenConfig platform exactly the same way. So there are differences. So, but then where is the value of OpenConfig platform if it's not the same everywhere, right? So.
Are you normalizing models, normalizing JSON at the moment to a particular model?
Yes, we do that, but let's say this is like a rat hole, you know. So you can do it to a certain point, but I mean the whole goal here is we should not do that in the future anymore, because if you look back today, how many SNMP MIPS are you using to onboard data? If you go towards Yang, I mean, going towards big data, it will be tenfold. And if you have to normalize all of the models, normalize the entire collection, that's a lot of work.
Yeah. Thank you.
Sure.
Okay, Robert.
Rob Wilton, Cisco. So thank you very much for this presentation. I think this is definitely where the industry needs to go to. So this is definitely on the right sort of path and things. So I think that's all great. I think the one question I have is in terms of how you correlate the data when you receive it. So if you have some network event like the interface going down, you're going to see obviously the interface going down as a notification, then you'll see like the traffic loss, you'll see the peers going away. What do you do to correlate that on the sort of client side when you receive that data up? Are you using machine learning for that? Or are you doing that sort of by hand to look at the timestamps and correlate over a short period of time? So what sort of mechanisms are you using to sort of correlate the data back into like a single event or know the source of that
problem.
Right. So let's say if you go 5 years back in time, we started with let's try machine learning and see what it works. But soon we discovered like, hey, actually that's not really bringing a lot of value because networks are rather deterministic. So if an interface goes down and you have BGP peering on top, you know what's happened next, right? So the BGP peering goes down, the withdrawals are there. So the only not deterministic part is actually somewhat the customer, you know, but even in the masses, a customer is predictable. So we ended up with a very deterministic network anomaly detection where these things are modeled. So basically we have a VPN service. We know on that VPN service what peerings are involved. We know the VRFs and so on. We know the dependencies. We accommodate that we are not receiving all the data at the same time, that we have a certain time window for aggregation and so on. And like a network engineer, so the more you see in the network, if you see state changes on your management plane, when you see changes in your control plane, but the traffic is still being forwarded properly, it might going through a different forwarding path, it's still okay. But suddenly, if the traffic is being dropped, so your concern gets more and more up, and therefore we're scoring that more and more up. And when you get the alert message, you want to show a network engineer exactly what you observed. You want to give him all the insights saying, hey, my topology changed. The forwarding device has changed. So at the end, basically with the scoring together, you can give him some help and say, I think you need to look at that. That might be concerning for you.
So just one follow-up question. So then it's still a case you've got like a manual step in the closed loop automation where there's somebody analyzing the operational data to then decide the action to take.
Right.
The next step potentially from there is to try and automate that. And I guess that's where it becomes more complicated in terms of making sure you're taking the right action.
Right. So I think the next step will be going towards transaction IDs. So NetConf already has like a transaction ID, but that's local to the device. So if you have like a global transaction ID for the entire service you're configuring, so you can observe basically that your topology changed, that your configuration changed, and you know that all these different configurations you deployed actually goes up to one single transaction. So now you can notify the network engineer and say, this is what changed on the network. This is what happened on the network. Do you consider rolling back?
Okay, thank you.
Jeff has one question, which you've been actually talking about, and then one comment. So back pressure and state compression obviously lead to a lot of issues with correlation. You've talked about how you're looking at things over a specific time window as a way to try to actually compress things down to an event. Is there anything in the modeling work that you're doing in terms of trying to actually say that this is, an inference that this occurred, based on an event that happened backwards in time? So routing change may have happened, but maybe it takes 10 seconds before it pops out in your routing plane, as an example.
Right. So in IPFix, you have basically when the accounting started and accounting ended, right? Mm-hmm. In Yang Push, you're probably referring to the periodical subscription, I guess. No, we did not go that far, but it's a good thought,
Okay. We've all lived in this problem, and this is just remaking it. And this is to my comment. So OpenConfig, I'm not a fan of a lot of things happening in the models, but that said, that's not the real issue. Comparability-wise, for the tool chains, GNMI is not what is trying to be done by Yang Push. So one of the things I suggest maybe for future versions of this discussion is that people start asking these questions, contrast a little bit about the fact that Yang Push gives you more of the state rather than sort of replicating all the bad sins of SNMP.
Exactly. Thanks.
Okay, thank you. Thank you. And now back to exciting topic of IPv6 extension headers, which actually caused some discussion in the chat room. So if you're not on the chat room, you might want to join. So Anna.
Hello, hi. So I'm Anna. I'm from the University of Aberdeen, where I work with Corey Fairhurst. Primarily, I work on wide-scale internet measurements to help guide protocol standardization. And today, I'm not going to update you on like any new measurements that I've done on extension headers. It's more of a meta talk on how we measure extension headers and what things to consider when measuring extension headers. Next slide, please. So IPv6 measurement is generally more difficult than IPv4 measurement. And that's due to a variety of factors, but mostly you have many networks that still don't support IPv6, especially in Europe. It's quite hard to find, to have IPv6 to your home or on your mobile network and so on. And then there's a problem of where you measure to. So you have all of these top 1 million domains lists, and once you resolve them, and once you filter them and get your unique IP addresses, you're going to find that lots of servers don't have IPv6, and that, as Nalini mentioned earlier, a lot of these domains are not very diverse. So you're going to have quite a few IP addresses concentrated into one AS. And finally, it's kind of hard to scan the IPv6 space. There are IPv6 hit lists, but of course, it's just much harder to do measurement on v6 than before. Next slide, please. Well, if you think IPv6 measurement is hard, then just think about measuring extension headers. Extension headers are a right pain. They got off to a very rocky start when IPv6 was first standardized. You had loads of routers that didn't necessarily support processing packets with extension headers in hardware. And because they were processed in software, that kind of opened up these routers to a DOS attack. And then from there, you just started getting loads of filtering of these extension headers. So they can be broken. So extension header traversal can be broken at many different places, and it can be a configuration policy, or it can be lack of device support. And next slide, please. Measurements have happened over the years, but because it's a pretty hard thing to measure, so no wonder you get so many different results. And there seems to be a consensus around these measurements that they don't agree with each other. Next slide, please. But then if you break them down a bit and you start to look at where you're measuring from and where you're measuring to, then you can kind of see how the measurements could in fact agree. Because there's so much brokenness, it really matters where you're going from and where you're going to when you do your measurements. By the way, if you've done measurements on extension headers and I haven't cited you here, do let me know and I will make sure to add you in a future version of this slide. Fun fact, most of the people who have done these measurements are actually in the room. Next slide, please. Right, so I'm going to show you different examples. Next, please. So I'm going to show you some examples related to where we measure from. Next. Where we measure to, and finally, how we measure. So, that's okay. We can go straight into them. Okay, right. So where we measure from is important, is especially important when you measure extension headers. Because you have different levels of transparency to different protocols, right? So if you're going to do a measurement campaign using a cloud provider, you'd better choose a cloud provider that is transparent to what you want to measure in the first place. So what I'm showing you here in this table is a measurement to the exact same set of destinations, and the only thing that is changing is the vantage point, is where you measure from, right? So you can see that some cloud providers just don't support hop-by-hop extension headers in the first place. Oh, by the way, all of the examples I'm giving are either the destination options extension header or the hop-by-hop options extension header. Right, so some cloud providers just don't support them outright. So these ones just, if you want to measure many different destinations, you can't do it from here. And even the ones where extension headers pass, you can see there's a wide degree of variability between different vantage points. And that's because to some extent, when you measure hop-by-hop extension headers, because so many of them get lost essentially at peering points, you're going to end up to some degree measuring the path from your vantage point, as opposed to all of those many destinations that you're trying to hit. Next slide, please. Right, so you need many different vantage points. So how do you do that? Well, you can choose a measurement platform like RIPE. And this gives you a bonus because RIPE essentially connects maybe 5,000, 6,000 different IPv6 vantage points. But they're all in access networks. So you can then see a difference between access networks and the internet core. I mean, the internet core is going to be more transparent to any sort of protocol traversal in general, just because there's less infrastructure there than there's less network devices that do weird things in the core than at the edge. But it's still very good to see what the split is. And because if there is a split there, then you can kind of start to drill into what kind of devices are there in an access network that aren't there in the core that could influence the result. So hopefully the table shows you there is a difference. Of course, there's a wide variability here as well, which brings me to my next point, which is destinations. Destinations matter as well. I mentioned earlier the top 1 million lists. Top 1 million domains list, rather. Well, always include a per AS split when you use one of them, simply because you have a lot of the destinations that are hosted by a small number of major hosting companies. So this table shows you the per AS difference versus the per host difference for the exact same list of destinations. So basically, if you look at it on an AS level, you see that, in fact, you get over 90% of the ASs that will support your packets with, in this case, destination options, extension headers sent to them. But if you look at the per host percentage, well, it can tell you a story that's worse than it actually is. Next, please. Okay, now this is data that is not mine, but it shows you a different point, which is that when you're measuring different destinations, always split them up by what they actually are, because again, your different destinations might have different types of infrastructure around them, like your web server might be behind the CDN and so on. So this is expertly presented here by RFC 7872. So you see the difference between web servers and mail servers and name servers in terms of traversal. Next, please. Then if you look at yet a different type of destination, which is destinations in access networks, measurements courtesy of AppNIC, they also tell a different story because you're measuring a different thing. Next, please. And then finally, we have Nalini's measurement efforts around FTP servers as well. And of course, different destinations, you'll see different results. Next, please. We're now moving into how we measure, and the answer to this is measure with as many different protocols as you can. I mean, there's not that many to choose from, but always try and do a UDP versus TCP split if you can. That's why I like to measure against DNS servers, because DNS servers, you can target them with TCP and UDP. And in the case of edge networks, for example, in here you can see it, a huge difference between, well, packets sent over TCP traverse less than those sent over UDP. And then this kind of lets you drill into the data a bit. You can start to think, why is this happening? Well, could it be because of loads of these edge devices mess with TCP? Like, for example, they read deep into the packet to get the MSS option and so on. And is this the link? Next, please. And then finally, you don't even have to measure that many paths. You can just measure the same path many different times to find something that is very unexpected. This is also measurements performed on RIPE. It shows you one path is measured with Paris traceroute. Paris traceroute aims to basically find different whether there are load balancers on a path by varying the different header fields. And if you measure the path with vanilla packets that don't have extension headers, with Paris traceroute, you find 4 different paths to your destination. You find 2 load balancers in there at least. But then if you rerun your Paris measurement and you use extension header packets, in this case it was a destination option extension headers that we sent, you find that, in fact, that path diversity is lost. So your load balancers on the path don't actually find the fields necessary to have that entropy to route packets on different paths. So this is a more subtle example of brokenness. It's not just drops, something else can happen. Thank you. Next slide, please. And I think I'm running out of time, but there's been many different results over the years, but if you take them together, they kind of tell a story. You can, even all of the measurements that I've mentioned maybe hit, I don't know, 4,000 ASs at most, and there's 120,000 registered ASs, right? So you're hitting, I don't know, 4% of the internet. Next, please. So there's more to do. Of course, measuring from different vantage points to many different targets in as many ways as possible will give you the best understanding of this particular problem space. And the areas I want to focus my measurement efforts on are whether or not forwarding decisions are influenced by the presence of extension headers. And I think my previous example kind of showed, sorry, kind of showed a hint of that a little bit. And also whether or not the network devices do read the extension header. And for that, some of these measurements I will continue to do from the RIPE Atlas.
You want next?
Yes. Yeah. So while most of the measurements I will still do from RIPE Atlas, I do have a giveaway. If you want this very handsome device in your data center, and your data center happens to not be in Europe or North America, I would be very happy to hand it to you. So just let me know. Next slide. That's it. Questions?
Hi, Anna. Thank you very much. Tom Hill from BT. I was just wondering about the picture on slide 12 with the different paths and the loss of resilience. Are you confident that all of those hops in there would actually be load balancers, or could there be something going astray with other types of traffic balancing? So, for example, LACP, ECMP, or even the first hop resilience protocols like VRRP or HSRP?
No, that's a internet path IP layer going from, I don't remember where the RIPE Atlas, where the source was. I think it was in the US. The destination was Zambia.
Sure. I was just thinking about the intermediate hops, if they were previously balancing and then...
So I don't think you'd be able to detect LACP from, is that?
Well, no, I mean, you can obviously usually with MTR and other tools like that see ECMP hops quite often, balancing across. If you're varying your source,
you would definitely detect this, yeah.
So I mean that points to, I mean we all expect that load balancers do strange things, TCP load balancers in particular, but that points to maybe there's an interesting conflict there with hashing on extension headers.
Exactly. Which headers do you hash on? And if you use an offset, which is maybe what's happening in that particular case, then you're not going to get the same device that you expect.
No, that's curious.
Or you're going to hit the exact same bytes every single time because your extension header is in the way, right? And I don't see, that's not an isolated case. I see that on maybe 30% of the paths that I measured.
No, it would be interesting if we could narrow that down to a vendor. Very interesting. As to the bit about the piece of hardware, some ideas on who I might be able to give that to if you want. So chat about that later.
Amazing. Thank you.
Now I put myself in the queue, and I'm just realized I don't know what's happening with flow labels when you do trace routes.
Right. So at first, RIPE Atlas will vary the flow label. So of course, the flow label will come before your extension header.
Oh, yeah, because I know that obviously if you have extension headers, you probably wouldn't be able to do load balancing by 5 tuples.
Yeah.
But some vendors, some software supports balancing based on flow labels. So I'm just curious how, like, because yeah, I don't know what flow labels is set for traceroute packets. So yeah, it would be interesting here to see if, for example, if you can play with that.
Exactly. And I have well, I would like to propose something for RIPE as a test they can include, because at the moment they vary flow label as well as source port, I think, 2 things. So if we can only isolate and vary one at a time in the Paris trace route, then we would be able to work out exactly which field is used. But this seems to indicate that flow label is used less than other things.
Okay, anyone else in the queue? In this case, thank you very much, Anna. It was very useful. I'm looking forward to see more data.
Thanks.
Yeah. Okay, so next. So, Benoit or Olga. Okay. Present. Just a second.
Hello. Good morning, everybody. My name is Olga Havel Huawei, and I want to share with you some experience that we gained throughout our POC that we did for modeling the digital map using RFC 8345. Thank you. We did it, and then we verified it with Swisscom and Telefonica and worked with them to ensure that some of the requirements identified and also that they are added to the POC. So in regards to IETF, everything is done right. We have young data model for network topology is the basic one. We have augmentations for layer 3. We have augmentation for layer 2. We have traffic engineering one. Next, please. Here is the young catalog status, current status with all the ratified, adopted, latest approved, and initial, and there are lots of drafts that are using network IETF network topology and augmenting them. Next, please. These are the RFCs, so we can see that there are only kind of 9 RFCs based on this. Next, please. And these are the current drafts that are being worked on. So there is a lot of activity around it in IETF, and we are looking at, next please. We are looking at how these modules work together. Can they work together? How they work together? Do these young modules work to create a digital map? We want to understand the relationship between topology, digital map, digital twin. And in our POC, we kind of modeled multiple layers using this IETF approach, and we want to share our experience today about open issues, requirements, etc. Next, please. So why do we need a digital map? Like we have a definition of digital twin in the draft IETF NMRG network digital twin architecture. And it's defined as kind of a virtual instance of the physical network, which is the twin, and that has the up-to-date information about the status, performance, and all the information about the physical network. And what digital twin does, it collects the topology data, KPI data, alarms, incidents, and also stores information about inventory, configuration, traffic engineering, planned data for what if, etc. So all of these data has to somehow be connected, including the actions and behaviors, and all of this data is at different layers. It can be device-specific, network-wide, customer service-related. So how to correlate all models and data in the digital twin? So via topological, we believe it's via topological entities at different layers, from physical to services layer. We identify all the topological entities, their relationships, and then we connect all of these different functional models and data via the topological entities. Hence, the digital map is the basis for the digital twin. It provides the basic model, meaning the model that has a minimum amount of information that is necessary to kind of describe the topological entities and relationship, and it represents a virtual instance of the topological information in the network, and it correlates all digital twin data into those topological entities. Thanks. Next. So I want to emphasize again that we believe the digital map provides the core multi-layer topology model, and this includes core topological entities, their role in the network at each layer, core properties. So those core properties are the ones that identify those entities and that are important at different layers. So, for example, at the device layer, that would be device identifiers, etc. At the routing OSPF layer, process ID. At VPN layer, VRF. So it is identified, layered identified. Also, relationship between those entities. We have relationships inside the layers, which would be interlayer relationships, and between the layer, like underlay, overlay, etc. So digital map model is a basic topological model that links all other functional parts of the digital twin and connects them all. And we know it's configuration, maintenance, assurance, KPIs, etc. Next, please. This is example from our POC, where this is just one example of three technologies, network and the routing layers, and how we used the IETF to model each layer. You can see by the bigger circle is the IETF network, node, termination point, and link, and by augmenting the core IETF network topology, we achieved implementation at different layers. Next, please. So we modeled the digital map entities, relationship, rules for instantiating aggregating entities, rules for instantiating relationship. We generated the knowledge graph that could be visualized and customized and extended. We modeled multiple layers from layer 2 to customer layer. We had layer 2 topology, layer 3 topology, IGP topology, it was OSPF, BGP, ISIS topologies. We modeled MPLS tunnels. We modeled SRv6, layer 3 VPN, and customer services at the top. And we modeled everything using RFC 8345 approach by augmenting it with different properties and types of the network. And we collected data from multi-vendor network. The POC is done in 2 labs, so we were able to kind of ensure that the approach we had was generic enough between the vendors and the labs. And during POC, we collected the requirements and showed the POC to the, as I mentioned, to the service providers and got their feedback. Thanks. Next, please. So these are some of the requirements that we collected and defined. So we need, for digital map, we need a basic model with network node link interface layers. It's provided by RFC 8345. It has to be layered from physical to customer service. It's provided by RFC 8345. It must be open and programmable, read and write for what-if scenarios. It's also provided by RFC 8345. It has to has standard digital map model and API. It has to be cross-domain. Both is provided by RFC 8345. We need semantic for layered network topology, and we have it in RFC 8345, but we do believe there is needs for some extensions there and improvements, so that is maybe the next step that we have to look at. Also for relationships are there, but maybe we need some more semantic there. But things that are missing and that have to be added is extensibility with metadata, how to plug to different functional modules, inventory, KPIs, SAPs, how to plug into SANE, intent assurance, etc. And not everything will be in Yang, so we have to plug into other models. Next, please. Specific observation for RFC 8345 is that maybe we need to extend it to have bidirectional links. Also for multi-point connectivity, maybe instead of unidirectional links, we do need some kind of higher level abstraction, especially for services layer, where you don't need to have all of the unidirectional peer-to-peer, it may be too complex. Then we need some additional supporting relationships. We only have supporting relationships from the node-to-node, TP-to-TP, network-to-network, but we do need TP-to-node and node-to-network, for example. Then we need additional semantic, probably. We modeled, currently we model tunnel and parts via RFC 8345, but there is, we lost some semantic that is available in the TE draft, so we have to look at how to take that semantic from the TE and add it. We modeled on all inter-layer relationships we are supporting, but we may need to add some semantic there. The relationship properties may be needed, the relationship subtypes. We also modeled using layers, but also sub-layers. So there is maybe some need to extend there. And also we want to add some kind of common roles, balance between simplicity but to focus on balancing, because our goal is to have very simple model as a core model for the digital map, not to go into kind of more complex models. Next, please. So these are some very high-level observations. We successfully modeled all layers in 2 different labs using RFC 8345. We modeled also the knowledge for aggregating entities and all of that outside of the RFC. We allowed for augmentation for different layers and technologies with some limitations. So our proposal is to allow for extending only with properties without extending for different entities, so that there is a kind of some common pattern in terms of different topologies. Principle is to focus on simple layered topological models. So the digital map contains only the core entities and the core properties at each layer. And some open issues that we have, there was a discussion whether there is a need of separation between layer 2 and layer 3 topology, because in some cases it can be represented with the same, but at this point we model them as a separate ones. It depends on the customer network. So in the case, for example, of LAG, there is a difference between the two. There is layers versus sublayers. We believe there is a need for sublayers as well, not just layers. And then there are some kind of still open issues around generic IGP routing that we got some requirements for versus basic OSPF, ISIS, BGP configurations. And we also have same technologies at different layers. So we could have BGP for underlay, BGP for overlay. So in that case, we may have to have same technologies at different layers. Next, please. So what's next for us? We will continue our POC, improving our POC. Here you can see also table of contexts. We will be working on the draft, and very soon we hope to share it with you. We want to also evaluate the technology-specific augmentation one by one from the IETF and share our comments with the authors. And we want to understand how to connect to other young modules. The highest priority would be how to connect to SAP module, but also to SANE, to inventory module for enterprises, to life cycle modules, so for all the other young modules that are relevant for digital twin and digital map. How to fulfill all the digital map requirements, meaning how to add metadata, etc., and report observations on regular basis to IETF. Next, please. So we are looking forward to your feedback. We want to know whether you think it's a valid problem. We would love to receive some digital map requirements from the service providers, because we want to ensure that they're included in our draft going forward. Use cases as well, and we are here the entire week, so please contact us if you're interested in this. Thank you.
Okay. Questions? Robert.
Rob Wilson, Cisco. So just a quick sort of question or comment on terminology. So you're using the term layers a lot. And initially I was thinking of layers in terms of device level YANG models, network layer YANG models, service level YANG models. But I think when you're talking about layers, you're just talking about that sort of network wide layer and your different sublayers within that layer. Is that correct? Am I interpreting that the right way?
When we are talking about layers, we are talking about different, starting from physical layer and then all the layers up to the service layer. which depend like underlays, overlays for the up to the services. So we would, that includes also the control layers and configuration of those. And this is for dependency of what service part, what it depends on, and capabilities then to provide full life cycle on top of those. So for example, our layers would be a physical layer, layer 2, layer 3, layer. Then we would have a routing, we would have tunneling, we would have, at the end, we would have a VPN service.
But maybe Ben was going to...
So there are different topologies in terms of physical and all the virtual topologies up to the service topology.
So, but is that all being modeled at the network layer rather than the physical devices, or does it include the devices as
We
well?
modeled all using RFC 8345.
Okay.
And RFC 8345 has four core concepts, which are network, node, termination point, and link.
Okay.
And we modeled all of those layers using those 4 points, and then relationships, supporting relationship and contain a relationship internally inside the layer.
Okay, I'll chat with you offline. Thanks.
Thanks.
Benoit Claes. So Rob, to also complement what Olga was mentioning, if you think about troubleshooting networks and closed loop and operational this, you need to understand exactly like Thomas was mentioning, you know, all the different incident correlation. And if you think about the service assurance for intent networking, the RFC that are in the queue right now, you have to see what depends on what. Right, so you got the service, it depends on a VRF, that depends on connectivity, that depends, etc. So the idea is, whenever we look at digital map, is to be able to map those layering of dependencies, right? And if you succeed to do that, that's what we're doing the POC, then we've got our digital map entities that are the same one as the intent assurance one. And whenever we succeed having that, we've got one view from the network and one view from the orchestrator controller. And we could correlate the intent that we see from the network and from the orchestrator. So the layering is actually the layering, the layering is actually the layering of the dependency of the services, because in the end we want to solve like service issues. That makes sense? I think so. Okay.
Thanks, Bernard.
Okay, I think the queue is empty. Thank you very much, Olga. It was comment on the chat from Eric Vink that your presentation and probably presentation from Thomas should be probably repeated to the wider audience this week in some working groups, I hope.
Yeah, I think we'll go with ops area.
Okay, cool. Thank you. So the next one is presentation, not a presentation, some short demonstration, as far as I know, about NTS. So Krista, are you around? Yeah, cool. Let me. So, you want to put it on my table if you want? Yeah. But I mean, yeah. Okay, yeah. If it's, I can just move.
We'll do it like this one, I guess.
Might be easier for you. So.
Does it work?
I do. Are you trying to? Are you a question?
Wonders of technology.
Okay. Okay.
There you go.
I remember how to do that.
It's all good, I think.
Let's see.
So now,
yeah.
Hopefully we should see a map here. Good. So my name is Christer Weinigel. I work for NetNode in Sweden, and we do something called NTS. So
close to the mic.
Okay, so we do something called NTS. So this is a map of the world, and the white dots are basically in Sweden are our NTS servers. The white dots in America, they are my test clients. So let's start with what is NTS? Well, NTP is the protocol for time distribution over the public internet. It's been around since the 1980s, but it's getting kind of long in the tooth. It doesn't have scalable security that scales to internet sizes. There have been sort of attempts to add scalable security, but none have really succeeded. So a few years ago, somebody started a protocol called NTS, Network Time Security, and NetNode got involved, I think, in 2018. I started working for NetNode in 2019, and well, after about 2 years in 2020, NTS ended up becoming an RFC, so it's RFC 8915 now. So, and NetNode, we're sort of committed to running NTS. So we have NTS servers, they're open for the world, and we're telling people sort of, please start using our NTS servers. So this is how it looked in February when we've been running NTS servers prototypes since, well, 2019, I think, when the first NTS implementation started appearing. And this is what happened in February, and we started just doing more. We set up our servers, and there's not much to say here. There's not that much traffic, but well, it's slowly increasing from 2,000 and then a bit more. So this is geolocation, of course, of users of our service. And as you can see, well, last IETF was at the 7th of November in London, and things started happening. So on the 7th of November, traffic increased to 10,000 hits per hour. That's not really much, but it's a tenfold increase from what we had before. Give it another week, well, we're up to about 100,000 hits to our NTS servers. And one fascinating thing here, by the way, is that if you look at the lights, they're actually moving across the Earth. They're actually following the daylight, and I don't really know why, but just a sort of interesting observation. And for some reason, it just kept increasing and increasing. So for me, this is really fun. It was a bit stressful too because our server started, I've been known to be at meetings and just telling people, well, NTS isn't going to take off for a while. It's new, it's only enthusiasts. And I really did have to eat my own words because our server started getting overloaded. The Linux kernel started throwing messages about being out of memory, out of sockets, that we were under a denial of service attack. And well, sort of Christmas vacation comes, we've sort of increased the CPU and amount of memory on our server, so we're sort of, oh, we're good. And then I went on Christmas vacation. And well, traffic kept on increasing. So I was quite calm here, got back from vacation, and suddenly we're up to 500,000 hits per hour. And for you who do networking more professionally, I don't have background networking, 500,000 hits per hour isn't that much. I mean, it's sort of only a couple of hundred requests per second, so it's not really that much. But for a fairly new protocol, I'd say it's quite impressive. So 7th of January, I got back to work again, and our servers were getting overloaded again. So me and our poor operations team had to scramble a bit and try to figure out how to make things run faster. I had problems because we were running this in Docker container, and the logging is single threaded, and the logging started to become a bottleneck. And then we're sort of up to 1 million hits per hour. And it keeps on like this. So a week later, on the 27th, when this movie ends, well, we're actually up to 2 million hits. So basically, this is not really tech heavy at all. It's just that NTS is a new protocol. It adds security, scalable security to NTP. And I'm quite happy that NTS actually seems to be in use quite a lot. So let's see if I can time this correctly. I was supposed to show a slide here. No, I can't even find my window. Oh well. Anyway, so a short summary is sort of basically NTS new protocol. If you're doing time over the network, please start using NTS because it adds security, and time is sort of important for quite a lot of protocols like TLS, HTTPS, DNSSEC. All of them rely on having good time. And well, so in about 3 months since October, November, we've seen sort of 1,000-fold increase in usage, which I'm really happy about. And it, for me personally, it feels quite good because it feels like, well, I'm making a small difference, making the internet more secure. And yeah, one more point is that if you look at this map, I've tried to sort of figure out how many users we have, and I'm not really sure, but in a day, I think we had about 5 million unique IP addresses. 20% of them were IPv6, 80% were IPv4. So most probably the IPv6 addresses are from hosts who are dual stack. So probably about 4 or 5 million unique users anyway. So I think that's about it. And well, if you look for my name, Christopher Einigel, please mail me at Netwood if you have any questions afterwards. Thank you.
Is it okay, Jen?
Yeah, Eric, yeah, sure.
I just wanted to say, Eric Klein, Responsible Area Director for NTP. I just did a quick check on the agenda. If you're able to make the NTP session,
I will be at the NTP session.
Yeah, I would suggest you please send the chairs.
Yeah, Karen talked to me and asked me to do this presentation at the NTP session too.
Okay, so the agenda is not up to date. Great.
So this is really light on technology, but it's just sort of, yeah, lovely. NTP is starting to be used.
I look great to seeing it again. Thank you.
Thanks.
Any more questions? Okay, thank you very much. Very interesting. And because we still have 20 minutes, I guess Randy is going to talk about RPKI.
My first comment is, of course, everybody wants to have a good time.
Okay, Randy, are you going to present, or you'd like me to control the slides?
I'm hoping to control the slides.
Okay, just a second. Okay. Being shared, hold on. Oops, was not me. Can you try again?
I'm requesting to share a deck.
Yeah, I granted you permissions, being shared.
I won't. How does it choose the deck that's on my laptop?
I think, I suspect.
Okay, I'll share screen.
Okay. Okay. We can see your screen, Randy.
This is good. Okay. So you can see my name comes last because other people did most of the work. Roman, the lead author, had to present this at an academic conference. And of course, they didn't know what RPKI was, so he had to describe it. He didn't use this slide. I might have. So just to get our stack straight, since we were talking about it earlier, the ROV and the RPKI, et cetera, are really on the management plane, go through the control plane and affect the data plane. The data plane is where the money is. But we're way up at the top trying to control the data plane where the money is. And there is a long path. So it kind of looks like this. And the kind of central yellow one's the key stuff. Where we do timing during this experiment as the clock ticks on the left. But we start at the RPKI portal at the RIRs, and we only measure at the RIRs. They issue the certificates. They put them in the publication points. The ISPs have relying parties, which are known as caches. Then the relying parties feed the routers, and then the routers affect the data plane. So we're timing this to try to see how it goes. The experiment, we got prefixes from all five RIRs, both 24s in V4 and 48s in V6. We announced them constantly from one AS that's connected to two upstreams that are ROV enforcing, and some direct IX connections, the Seattle Exchange, which don't enforce ROV. Then a secondary sub-experiment was a set of write prefixes from three ASs scattered around the Asia Pacific, fed by non-ROV upstreams. These measurements were taken over 11 months. These are so we used ROAs as beacons. So at each RIR, if they had an API, we drove it by the API. And if they didn't have an API, it was GUI scripting garbage, which is horrifying, and created and deleted ROAs. There were two sets of prefixes. One set was control ROAs. They were always valid, validating BGP. Remember, the BGP is constant. So there's a set of 24s and 48s, which were always valid. Then there are test 24s and 48s that always have an invalidating ROA. But we announced a validating ROA for half a day, once a day. Now remember, if there's an invalidating ROA and a validating ROA, the validating one wins. So what we're doing is toggling valid, non-valid, half a day each for half the prefixes, and then half of them are controls. They should always be valid. So we look here at rogue creation delay. There's the signing delay. It's the first column. APNIC is 10 minutes. And that's because they seem to batch signing in 20-minute intervals. So therefore, the mean signing delay is 10. And then we look at the not befores. That's okay. Okay. And then we look at the publication. And it goes nuts for Aaron and Lacknick. And so we did some research and we looked at the difference between the signing time and the publication time. And it turned out Aaron and Lacknick had their HSMs running in GMT, of course, but their servers were running in their local time zones. I used to work at AT&T. They had their entire global infrastructure running on New Jersey time. So this did not shock me. We wrote to them both, of course, and we talked to them, and they fixed it, or they did workarounds, okay? The relying party times are not too shocking, but 15 minutes to get all the way, or 20 minutes to get all the way to BGP is a little slow. You're talking about BGP being much faster, okay? So the creation delay had the medians for a few minutes to over an hour to the publication points. And we know of at least one NIR in Asia Pacific that publishes once a day. Okay. So to measure the relying parties, we used one instance of RP software that's public. Philip Smith did some measurements on how RPs vary, worth looking at. We did not run RPKI router because we were more interested in the effects on real BGP. Okay. And some RPKI relying parties have not discovered fork and exec, so they do head of line blocking for bad publication points. The rice rip collectors we got used to see when the BGP was actually published. Okay. If the control prefix was missing, that means the test prefix data is no good, don't measure it. So we're looking for BGP effect. We used RC00 and RC01 because there have been studies to show that you can add more and more collectors and it really doesn't make much difference. The biggest difference would be adding Sao Paulo, which we didn't do. This has all the biases discussed for many years about using the route collectors, but this is good basic data. Okay. The revocation delay, in other words, when the ROA when the validating ROA is withdrawn, how long does it take before the relying party gets it? APNIC's delayed again, okay, and there were RPs that were hanging as I described, okay. This one starts to get interesting. There you see, so here we have a CDF. What we have is delay for different prefix types, different AFI-SAFIs, different RARs. And here you get to see Aaron and Lachnick's time zone bugs. Okay. And you'll see it's kind of asymptotic to 1. And the reason for that mess up there is sometimes it never really reaches because RPs, and what's worse is the RIRs get stuck. We had a case where a APNIC prefix, the user interface told us that the ROA was withdrawn, but in fact it was still at the publication point. And that happened across a number of RIRs. Okay. Withdraw is slower than announce. But if you compare those two, you see it really. The reason is most of the big ISPs, or even medium ones, run 2 relying parties. The routers are fetching from both. They're equal priority. And there's this phenomenon you need to think about, which is if either of those relying parties has a validating ROA, then the router gets a validating ROA. So both of them must have received the withdrawal for the router to have decided the ROA is dead and the prefix to go invalid. So this is the difference in propagation between the 2 relying parties at providers. Okay, so this is, again, all of the router's AS's caches must have received the withdrawals before the withdrawal is effective. Okay, Sprint, so here we see NTT upper, Sprint lower. Okay, we see much of the same phenomenon. The Sprint slower curve is because their RPs pulled less frequently and they had damaged RP software. The variety of software out there varies greatly in quality. I'm trying to be polite. Sprint gets an earlier start because their routers pull their caches more frequently than NTT's, even though their caches pull the global RPKI more slowly. And these phenomena were reported, discussed with Sprint and NTT. And of course, they worked on their software, they worked on their polling rates, so things improved over time. Okay. User query, that means the RIR was updated versus BGP across a number of ASs, and most operators here will recognize those. and notice that, some ASs are pretty good, pretty quick, and some are rather slow. And the reason, by the way, that we really care about this is if I make a mistake and have a row that invalidates my prefix, how soon can I get the fix out? So these draws, as I said, are much slower because of the dual caches or multiple caches. And there's that stuck row bug again. Okay, and 6830 got bitten by it, but so did Sprint 1239. Okay, so we then ran traceroute from a cloud of Atlas probes to the test prefixes every 15 minutes. Surprisingly, the results are pretty much the same for BGP. But what's fun is you can see path hunting. And I've kind of circled it in blue. Okay. And so you can see that at the red stripes are the withdrawals, by the way. And you can see where when the withdraw, it's doing path hunting and finding paths, but until it's withdrawn at all the and then it goes back to 0. Okay, so the RIR delay, and there's the ISP delay. The ISP delay looks significantly bigger. Iron and Lacnic, of course, are now fixed. Okay, but look at those ISP delays, 15 minutes, 30 minutes. Okay, so if I make a mistake up there, how quickly can we fix it before I'm losing money? BGP propagates in minutes. RPA propagates on the order of an hour in bad cases. Time to repair is bad. Time to authorize a DDoS mitigator may take actually longer than getting a contract in place. There were the HSM time skew. Okay. Bad RP software. And this is a new one. I'm not going to go into it here, but if you dissect ROAs, you will find the anatomy between them varies. Okay. The limitations of the study, the lying party software was so-so. We did not measure RPKI to router, but that's notified driven, so it should be fast. My family has jokes about should be. We did not measure delegated CAs, just the 5 RIRs. And RIR screen scrapings and even APIs seem not entirely reliable. This paper was presented earlier this week at PAM. Okay, what do? Well, CAs and RIR should publish more frequencies. RPs should poll very frequently. Use RRDP, please. Let's stop this rsync stuff. And we have another study measuring it, and there's a bunch of rsync still out there. There are clients that can still only rsync. As protocol designers, BGP switching to away from the current RPKI transports is something that should be looked at. But only 2 of them have been looked at so far. BGP has a dangerously shared fate, and we can go down that rabbit hole, and it's fun. And remember, by the way, BGP is unordered. In fact, reordering is guaranteed. And timing skew is significant. Back in, I think it was 98, Tony Lee and, God, I'm forgetting who else, looked at using the DNS. The problem basically is DNS does not handle aside from propagation, all these issues. It's also a pull protocol instead of a push. But DNS does not handle make before break. In other words, if I want to switch from Sprint to MCI, I can't put out a roll for MCI before I withdraw the one from Sprint. So, a warning. Bert Hubert, back 5 years ago, put out a paper called The DNS Camel and the Rise in DNS Complexity. 18 years earlier, I presented at the IETF plenary, not using a camel. It was an old horse. Warning, the DNS was getting more and more complex. We are doing this to the RPKI. Before this thing works well, we really need to not overload it. I just want to thank these folk for giving us donated rack space, bandwidth, kit, etc. And questions?
Okay.
I made
Thank you,
it.
Randy.
I
We
made
have
it.
1 minute.
I made it.
1 minute for question. Please be brief. I guess you can take the discussion offline if it becomes too interesting.
Hey, Randy, this is Jeff Haas. Did I miss in your slides whether you had any statistics about convergence time for individual AS number as part of this?
Yeah, there was one slide on a particular set of ASs.
Thank you. I'll go look for it.
Brad Gorman and Aaron. Hey, Randy, do you have any of the updated slides after the fix was implemented?
I'm not I don't think we put specifically slicing the time differently either in the paper or in the slide deck, no. But you essentially fell in line with everybody else.
Thank you.
Hi,
But
Randy.
your workaround worked. Hi, sorry. Go ahead.
No, that's okay. Sen Chai from APN8. Just want to say thank you for the info. Since we learned about this, we've been looking at changes and fix for the delay. Thanks for the info.
Sure.
Okay, thank you very much, Randy. Perfect time management. We're just 1 minute late. Thanks, everyone. See you in, what is, San Francisco? What's the next one? Yeah. See you there.
Is the chat saved? Because I didn't get to read it.
It gets stuck in the echo and the meeting stuff. So yes, it is saved.
Thank you. Good enough. Warren, when you get a chance, if you'd send me a pointer to it. Or I can go to, I'll dumpster dive. Okie doke. Thank you. Get well, Warren.
I don't think we met before, right? Tim. Well, I'll see you tomorrow. I think I'll join you for lunch. But,
Talk tomorrow.
yeah, all right.
Okay, take care.